This is a mathematical slide. I'll do it step by step. There is absolutely nothing mysterious about it. Okay, so this is the quantity we've been talking about. This is the probability of a bad event. But in this case, you realize that I am putting G. Remember, G was our final hypothesis. So this corresponds to a process where you had a bunch of H's, and you picked one according to a criteria that happens to be an in-sample criteria, minimizing the error there. And then you report the G as the one that you chose. And you would like to make a statement that the probability for the G you chose, the in-sample error, happens to be close to the out-of-sample error. So you'd like the probability of the deviation being bigger than your tolerance to be, again, small. Okay? So all we need to do is find a Hoeffding counterpart to this, because now this fellow is loaded. It's not just a fixed hypothesis and a fixed bin. It actually corresponds to a large number of bins, and I am visiting the random samples in order to pick one. So clearly that the assumptions of Hoeffding don't apply that correspond to a single bin. Okay. So this probability is less than or equal to the probability of the following. Okay, I have M hypothesis, capital M hypothesis. H1, H2, H3, HM. That's my entire learning model. That's the hypothesis set that I have. Finite, as I said, I would assume. Okay? So if you look at what is the probability that the hypothesis you pick is bad, well, this will be less than or equal to the probability that the first hypothesis is bad, or the second hypothesis is bad, or the last hypothesis is bad. That is obvious. Okay? G is one of them. Okay? If it's bad, one of them is bad. So this is less than or equal to that. Okay? This is called the union bound in probability. It's a very loose bound in general because it doesn't consider the overlap. Remember when I told you that, okay, the 0.5% here, 0.5% here, 0.5% here. If you are very unlucky and these are non-overlapping, they add up. The non-overlapping is the worst case assumption, and it is the assumption used by the union bound. So you get this, and the good news about this is that I have a handle on each term of them. The union bound is coming up. So I put the ors, and then I use the union bound to say that this is equal to, and simply sum the individual probabilities. Okay? So the half plus half plus half, 0.5% plus 0.5% plus 0.5%, this will be an upper bound on all of them. Probability that one of them goes wrong, probability that someone gets all heads, and I add the probability for all of you, and that makes it a respectable probability. Okay? So this one, the event here is implied. Okay? Therefore, I have the implyment because of the or, and this one because of the union bound where I have the pessimistic assumptions that I just need to add the probabilities. Now, all of this, again, I mean, we make simplistic assumptions, which is really not simplistic as in trivially restricting, but rather the opposite. We just don't want to make any assumptions that restrict the applicability of our result. So we took the worst case. This is it cannot get worse than that, right? So if you look at this, now I have good news to you, because each term here is a fixed hypothesis. I didn't choose anything. Every one of them has a hypothesis that was declared ahead of time. Every one of them is a bin. So if I look at a term by itself, Hoeffding applies to this exactly the same way it applied before. Okay? So this is a mathematical statement now. I'm not looking at the bigger experiment. I reduce the bigger experiment to a bunch of quantities. Each of them corresponds to a simple experiment that we already solved. So I can substitute for each of these by the bound that the Hoeffding gives me. Okay? So what is the bound that the Hoeffding gives me? That's the one. For every one of them, each of these guys was less than or equal to this quantity. One by one. All of them are obviously the same. Okay? So each of them is smaller than this quantity. Each of them is smaller than this quantity. So now I can be confident that the probabilities that I am interested in, which is the probability that the in-sample error is being close to the out-of-sample error, is like the closeness of them is bigger than my tolerance, the bad event, under the genuine learning scenario. You generate marbles from every bin, and you look deliberately for a sample that happens to be all green, or as green as possible, and you pick this one, and you want an assurance that whatever that might be, the corresponding bin will genuinely be good out of sample. That is what is captured by this probability. That is still bounded by something which also has the exponential in it, which is good. But it has an added factor that will be a very bothersome factor, which is, I have capital M of them. Now, this is the bad event. I'd like the probability to be small. I don't like to magnify the right-hand side, because that is the probability of something bad happening, okay? Now, with M, realize, okay, if you use 10 hypotheses, this probability is probably tight. If you use 1,000,000 hypotheses, we probably are already in trouble. There is no guarantee, because now the 1,000,000 gets multiplied by what used to be a respectable probability, which is 1 in 100,000, and now you can make the statement that the probability that something bad happen is less than 10. Yeah, thank you very much. We have to take a graduate course to learn that, okay? So now you see what the problem is. And the problem is extremely intuitive. In the Q&A session after the last lecture, we all got through the discussion the assertion that if you have a more sophisticated model, the chances are you will memorize in sample, and you are not going to really generalize well out of sample, because you have so many parameters to work with. There are so many ways to look at that intuitively, and this is one of them. If you have a very sophisticated model, M is huge, let alone infinite. That's later to come. That's what the theory of generalization is about. Okay? But if you pick a very sophisticated example with a large M, you lose the link between the in sample and out of sample. So you look at here. Okay, I didn't mean it this way, but let me go back just to show you what it is. At least you know it's over, so that's good. Okay, so this fellow is supposed to track this fellow. The in sample is supposed to track the out of sample. The more sophisticated the model you use, the looser that in sample will track the out of sample, because the probability of them deviating becomes bigger and bigger and bigger. And that is exactly the intuition we have. Okay.